In this video, we're going to continue our notes on optimization and the first and second derivative test by looking at concavity of a graph. So here we are, testing for concavity. So concavity tells us about how our curve or our graph bends. So you may have seen this before in a previous class when you've looked at parabolas. So parabolas have the shape, I'll just draw a little cartoon for us. This way, facing upward or downward. So overall, when our graphs have this first shape, opening upward like this, we call it concave up. When our graphs look like this, kind of open downward, we call it concave down. But we have some more formal, rigorous ways of describing these different shapes of graphs. In particular, concavity deals with how our graph increases or decreases. So before looking at example 8, let's take a look at what we are going to call the second derivative test. And before we do that, I'm going to ask you to pause the video and describe some graph behavior for me. So what I'm going to do is draw 4 sets of axes. And what I'd like you to do is draw a segment of a graph that is representing each behavior that I'll outline. So in the first two, draw 2 different graphs that both increase. Draw this first one so that the increase is at an increasing rate so that it gets steeper and steeper. For such a graph, we call it concave up. In the next graph or segment that I'd like you to try to draw here, draw a graph that increases but at a decreasing rate. So the increase slows down. So that we call concave down. In this next axis here, I'd like you to draw 2 different graphs that both decrease. But in the first one, try to draw a graph that decreases in a way that's slowing down. So the amount of decrease gets smaller and smaller, which we call concave up. Then in the last graph, draw a graph that decreases, but at a quicker rate. So that the decrease gets larger and larger, which we call concave down. So I encourage you to pause the video, get out your pencil, draw some ideas, and then we'll pick it up together and look at how we could draw each such graph behavior. All right, so let's look together. So first two graphs, we want our graph to increase. So that means wherever it starts, we want it to get larger. I'm going to draw the starting and ending point for both graphs. So increasing, we want it to be concave up, or we want the amount of increase to get larger and larger. So that means we want to start increasing and then increase even more, like this. This next graph, we want to slow down. We still want to increase. So we want to start increasing a lot and then not a lot. So we see that even though both of these 2 graphs are increasing, they're increasing in different ways. One way we call concave up, one way we call concave down. So what's different about the 2 ways in which these 2 graphs increase? Well, as I said in this first one, concave up, we want the amount of increasing to get larger and larger. So what's happening for such graphs? Well, we know that the derivative f prime for such a graph is bigger than 0. And that's true for both of these graphs because our graph is, or our function is increasing. But in this first example, the amount that the graph increases, so if we look at little chunks of increase, it gets larger and larger. So the derivative itself is actually also changing at a larger rate. So that means if we look at the changes of the changes, these changes of these different changes are getting more so and more so. So if we compare how much these changes are changing, we have a larger change in each case. So that actually deals with the second derivative. So in a case as this first example with a concave up graph, our second derivative is also positive. How is that different in this next example? Well, if we look at our changes, the changes of the output values, those changes get smaller and smaller compared to each other. So for such a graph, the second derivative, f double prime, is less than 0. That's also going to be the story with these next two graphs about how we can draw two different graphs that decrease. So I'll go ahead and get you started here, drawing a point where we start and end. And I'd like you to try again, if you haven't already, to draw two such graph behaviors. Awesome. So for this first graph, you should have drawn something that looks like this. This next graph, something that looks like this. And what do we notice about these two graphs? Well, their first derivative is less than 0. And that's because our function is decreasing. But if we look at the changes of our graph, so our change first is this maybe amount in the first little chunk, and then again, get smaller and smaller. The changes that we see in our graph are getting smaller also. So the second derivative is also less than 0. Oops, and I just miswrote that. So again, we're looking at how these changes are the derivative changes. And if we're at first going larger and then smaller changes, we're slowing down. So that derivative, second derivative, is less than 0. Oh, I said that same thing again. Let's fix this. Bigger than 0. There we go. And in this last curve here, we see that our derivative or our changes are getting larger. So our derivative is speeding up. So our second derivative here is less than 0. And this is the case because we're decreasing in each case. So those changes are actually negative. Okay, but I just want to summarize what we've done here. So if we look at our two graphs that are concave up, well, what is the same about each of these graphs? But their second derivative is bigger than 0 or positive. So a concave up graph means that the second derivative is bigger than 0 or positive. When we have a concave down graph, the second derivative is less than 0. So in these two different types of behavior, concave up or down, is determined by the second derivative, whether the second derivative is positive or negative. So we can summarize this here in a rule that's often called the second derivative rule. And so that just states what we've just seen here in the images that we drew. So that is that if f double prime of x is bigger than 0, then the original function f of x is concave up. If the second derivative of x is less than 0, then the original function is concave down. So in the first derivative test, we looked at the function, our original function f, whether it was increasing or decreasing. In our second derivative test, it tells us if our original function is concave up or down. And so here we have some consequences of our function where the second derivative is either positive or negative. But then what happens when our second derivative is actually 0? Well, when our second derivative is 0, it's called an inflection point. So I'll write that down here. So an inflection point happens where our second derivative is 0. So I'll say, similar to the language of a critical value, C is an inflection point. Actually, I'm going to change this a little bit because for an inflection point, we care about both the input and the output. So I'll say C comma f of C is an inflection point if f double prime of C is equal to 0. We actually have another situation, or f double prime of C does not exist. And this is similar to that first derivative rule. We could have a kind of a vertical tangent behavior at that point. And so in other words, that inflection point is where concavity changes of f. So inflection point, so that means at c comma f of c, concavity may change. To be a little bit more specific, concavity of our original function. Oops, here we go. Concavity of f may change. Excellent work. All right, in the next video, we're going to look at the next examples to help us become more comfortable with this second derivative test.